let's learn how to analyze op-amp circuits. So what's drawn on the screen here is like one of the simplest but actually useful op-amp circuits. So the structure of this is we have input voltage, which we've represented by this voltage source. We're calling that Vin. We have output voltage on the right hand side here, which we call VO. We have two resistors, so RS and RF here are the two resistors, and of course we have our op-amp in the middle. And this thing is called inverting amplifier circuit. So it's an actually useful design, and we're going to see why it's useful as we go through and analyze it. But let's learn about the steps that we need to follow. So the steps to analyze a circuit like this. So step one is to check for what's called negative feedback. So negative feedback means the following. It means there is a resistor or resistor network connecting the output. Okay, so the output is this bit, connecting the output to the inverting input. So the inverting input is the one with the minus sign. So that's the inverting input, and we can see in this circuit that there is such a path. So it runs through here, and so because we have this path, it means this circuit exhibits negative feedback. So negative feedback is the good kind. It's the kind that we want. And so because we have that, we can proceed with the rest of these steps. If you do not have negative feedback, you need to do something a bit different with the analysis, and we'll talk about that later. But for now, the good case, the happy case, is that we have this negative feedback. So continue. All right. Then step two. If we have negative feedback, then the op-amp will ensure the following things. So we can make these assumptions. So the first thing that we assume is that the current that flows into the input is 0. So IM and IP, which are the currents flowing into the minus and plus terminals, we assume that those currents are equal to 0. Now, in real life, there's some small current will flow, right? But we're dealing with an ideal op-amp circuit. So this makes things easier if we assume that there's 0 current. Then the next thing that we assume is that the voltage at the negative terminal is equal to the voltage at the positive terminal. And this is kind of magic, right? This is because the op-amp is providing negative feedback. So negative feedback means that if this condition was not true, there would be some sort of error, right? Some difference between these inputs. The op-amp will then work to reduce that error. So work to make this condition true. How does that happen in practice? Well, if you look carefully at this circuit, you can see we have an output voltage is connected through a voltage divider circuit. So what the op-amp is doing is choosing an output voltage such that the voltage divider circuit works out to be this condition of having equal voltages here. So there's actually a lot going on. This op-amp is doing quite a clever job in actually making these voltages equal. So we make that assumption, and then all of a sudden we have a much simpler system to analyze. Once we've done that, then we write Kirchhoff's current law at each node and then solve. And that's pretty much it. So let's run through these steps for this particular circuit. So step one, we check for negative feedback. Yes, we see resistor network connecting the output to the negative input, to the inverting input. So yes, good, we can proceed. Step two, we assume the currents are equal to 0. So IM is equal to 0 and IP is equal to 0. We also assume that the voltages at these pins are equal. So for this circuit, I look at it here and I see VP is equal to 0, right? It's actually directly tied to ground. So VP is 0. Therefore, VM is equal to 0. That's really important information. That's going to help us a lot in analyzing this circuit. Next step is to write KCL at the node which is labeled VM. So if I do that, then I will have the following equation. So I will have voltage VM minus V in, so I'm looking at the left-hand branch, this one here, divided by RS. So that is the expression for the current that leaves VM to the left. That plus the current that leaves VM to the right through the other branch would be VM minus V out divided by RF. And that is equal to 0. It's equal to 0 because we also assume no current flows into the op-amp inputs. So from here, we're actually nearly there. We can take our information that we learned about our voltage VM. We know VM is equal to 0. So we can substitute VM is equal to 0 into this equation, and we will get negative V in divided by RS minus V out divided by RF is equal to 0. And so we're pretty close. What we would really like to know is, well, what is the output voltage? So I'm going to solve for the output voltage. So I have V naught over RF is equal to V in divided by RS. If I multiply by negative RF, then I will get negative RF divided by RS times V in. So what does this mean? What does this tell us? So therefore, the output voltage is proportional to the negative of the input voltage with a gain of RF divided by RS. So by choosing values for these two resistors, we control how much the voltage will change from input to output. So we've built an amplifier circuit. I choose appropriate values for RF and RS, and then I take my input voltage and I make it bigger or smaller, and I also make it negative. So I make it negative, but I change the magnitude according to the ratio of these two voltages. So this design is called an inverting amplifier. Right, so it's an amplifier, but it also inverts, right, makes negative the signal. So this is a real circuit. This is something that people actually use, and it's probably the simplest sort of op-amp design that we can analyze to explain our steps. So let's summarize the process. If you had a more complicated op-amp circuit, what would you need to do? So step one, you check for negative feedback. So negative feedback is where there's a resistor network that provides a pathway for the output voltage to affect the input voltage at the negative terminal. And if there is such a pathway, then the op-amp is going to find a way to choose the output voltage such that the two inputs are equal. If you don't provide this feedback path, there's no way for the op-amp to create this situation that the voltages are equal, and this analysis method is not going to work. So we must have that feedback path. Then, once we have that feedback path, we assume no current enters the op-amp terminals, and we assume that the voltage at those terminals is equal. And from there, it's pretty much routine circuit analysis, and you can then solve for what will be the expression for the output voltage, which is usually the thing that we're trying to find. So we usually want to know what will be the output voltage as a function of the input voltage. And that's your op amp circuit.